Hi everyone. We're going to talk about the demonstration. Hopefully you watched that first. And I took a couple of, frames I pulled out of the video just so we could talk about it. And then we're going to talk about atomic emission and the Bohr model in this content module. Um, so we did flame tests for metal atoms, and hopefully hopefully it came across a little bit in the video. It actually, when you look at it here, the pictures turned out better than I thought the video did. It looked a lot better in person, as I said, but the fireball part of it, um, that's a lot of fun to do in person because you get a big flaming fireball. And it's one of my I did this demo, and I've never actually done a presentation where I'm using my webcam pointing at my screen, but I don't have a color printer. So I, do what you can do. You kind of MacGyver it. And so anyway, the flaming fireball version of this, where I sprayed it into the torch, I did that a long time ago. I used to do it on the first day of class just for fun. Um, and so, you're not going to get the same effect watching a video of it, but it's pretty cool. But then a few years later, I discovered a way to do these flame tests that works with a large classroom. Of course, a lot of you probably did flame tests in high school, where you take the little metal wire and dip it in salt and stick it in the Bunsen burner. And it's awesome. I love doing that. But this is something you can see in a class of 200 to 300 students, and it's kind of fun. Anyway, I didn't think that the video worked very well at all compared to seeing it in person. You just couldn't see the colors. This is with the light on, and I did notice with the light on you could see the green pretty well way up there. But then with the light off, it's just too bright. But if you look at it closely, when I just pulled out one frame, a picture out of the video, the flame test worked really well. Here we've got boron with the green, we've got sodium with that orange color, and potassium looking purple. So not bad, actually. It really worked pretty well. I think the copper had basically burnt out by that time. You might see a little bit of the copper never really, I couldn't see it very well in person either. I don't know if I did something wrong there, but it's supposed to be kind of a bluish green, kind of turquoise. You can sort of see it there. But anyway, so now this has got to be the awkwardest content module of all time. I guess I'm awkward no matter what. But now I got to flip it around because I'm going to write on the paper, right? So anyway, here we go. Bear with me. I usually get it eventually. Having a little bit more trouble today than I did the last time. I'm not sure why. Oh, I think I've got it spun around. Oh, for goodness sakes. I should probably just re-record this because this is not going well. I think I got it. Doesn't look like much to you, but at least I can spin it around now. All right, well, hopefully, if we're in person and I do stupid things, the class usually enjoys that. I don't know if I'm not getting, obviously I get no feedback this year teaching. So anyway, here I am. I should probably load this into a video editor and cut that out, but I just don't have a couple hours to do that. So sorry. Atomic emission. So I think atomic emission is really cool, and that's what we're using. Remember, the whole big picture of this is the interaction between light and matter, or electronic orbitals in atoms, and using that to, kind of explain the orbitals and eventually electronic configurations and the periodic table. That's the big picture. It's like chapter 7 is a lot of the chemistry, right? A lot of the chemistry that we had to kind of memorize in chapter 2. So that's where we're headed, is towards electron configuration and orbitals. All right, atomic emission. And I like to just talk through this with the class. Of course, the book has it very carefully laid out in the text and figures. So here's the idea. Um, we have, let's pull this up a little and then get it. We have energy on going, increasing that way. And then we have these energy levels, discrete energy levels. So I'll just represent them like that. Yeah, I'm going to switch and go back to the marker, make it show up a little bit better. All right, so that's energy going up. And we're going to represent an electron just as E minus. And later on, we'll talk about why we represent an electron with a one-sided arrow. But in this flame test, what was going on is we're heating it up, right? I lit the methanol on fire, and some of the atoms get up into the vapor phase, and they're really hot. And what that does is it's enough energy to promote that electron to a higher energy level. So this is adding heat. And so then the electron, if we just kind of go as this progresses, we redraw this. Now we've got the electron up here, and we call that an excited state. So that's an excited state. Oh, it's my brother's birthday. That's what that was, that alert. Anyway, oh, this has got to be the worst one ever. Sorry, guys. So, electrons promoted to that excited state, a higher energy level, and then what goes up must come down. So it can't stay excited for, and it is going to then drop back down to the lower energy level that we call the ground state in this case. Now, when it does that, so that electron going back down is called, in this case, there's lots of ways an electron can get down to the lower energy level. But in this case, what's happening and what we're seeing is we're seeing light given off. So plus a photon. And that photon then has a very specific energy. And that specific energy is, let's see if I can get this all on here, the difference in energy between those two levels. So that's that change in energy, okay? And the way this works then, the different atoms are going to have different energy levels based on their orbitals. And so that change in energy will be different for different elements. And that then is equal to the energy of the photon. So it has to match exactly. This distance in energy, the difference in energy between the two orbitals, the two energy levels, has to exactly match, or does exactly match, the energy of the photon that comes off. And so that, the energy of the photon is E equals h nu, right? That's what we did in the last one. And so that difference in energy between those two levels is equal to h nu, or we can also get wavelength, and the wavelength is what we usually associate with the color. And so this idea then is that these energy levels are orbitals in the atoms for electrons. And that's what we're studying in chapter 7. All right, let's see if I'm back on track. Okay, so this is another figure from your book, and of course it is in color. I'm not going to shine it back up on the screen. This handout is posted, and of course you have the figures as well to look at. But we just want to look at the process here. So I'm not going to say a whole lot about this one, but I'm going to focus it in a little. You can read it. There's two things going on here, right? Up here, we just have a light that's giving off white light, so an arc lamp or something. And if you shine it through a prism, I don't know if a lot of you have seen a prism, but it just spreads the light out into its different colors, different wavelengths. And so you'll see the rainbow on there. And you can do this yourself if you have a CD. No, nobody has a CD anymore. Take a DVD and flip it over and look at the back of it underneath some light and twist it back and forth, and you'll actually see the rainbow there. I should probably could grab one and try it right here. You might actually see it. You need a kind of a bright light source, but that's you know, diffraction off of that. You see the different colors of light, and so white light can be split into all of its component colors, just like when you see a rainbow. That's what happens. Well, what they did is they took a hydrogen lamp. So it's got hydrogen gas in here, and it's an arc lamp. And, you know, just like we did, just like I did in the demo with the metal atoms, it would get hot and emit light. And then you can see, nobody has photographic film anymore. We all have digital cameras. But on a piece of film, you can see bright spots that correspond to this light from hydrogen being split out into different wavelengths. And it's not all the colors like from a white light source. It's just very distinct wavelengths, very sharp lines. And down here, you can see 410 nanometers, 434 nanometers, 486 nanometers, 656 nanometers. It doesn't show up here. It'll show up in the book and on the handout. And so they're very discrete lines, and they sorry, I didn't dismiss that correctly, and it's going to keep reminding me to wish my brother a happy birthday. I think I would just remember. But all right, sorry. So those wavelengths, those emission lines are super sharp, super narrow. It's a very discrete light source. And that's because that wavelength has to exactly match the energy difference between these two energy levels in the hydrogen atom. And so this is only showing one of those. Usually from an atom, you'll get several different orbitals that it can emit light from. And so that's what we're seeing in hydrogen emission. And then this is the book's good representation of it, showing the various energy levels for hydrogen and change in energy, just dropping down from all those different electronic orbitals. And that's the colors of light that you see. All right, so we could take the colors that we saw from, sodium, boron, and potassium and figure out then what's the energy of that photon coming off, of that light coming off from those atoms. All right, so that's the idea. Okay, so the model then that we're going to use, there's two models that we talk about. One we're going to do in this content video, and another one we're going to do later on. So I'm going to try with just the pen and see how well this works. But I want to talk about models in general. And so I've got a little sticky note to remind myself to say this. All models are wrong, but some models are useful. Okay? In other words, a model it's incomplete, and we're always refining it and improving it. But this first model that we're going to talk about is the Bohr model, named after Bohr. I've heard that it's really boring, but uh, it's important to talk about it, even though the first thing I'm going to say about it is that it's incorrect. So it's important. This model is incorrect, and it's a model that a lot of people have in their heads for how electrons exist in atoms. Here's the model, but the reason we talk about it in Gen Chem is because it really was a major breakthrough in thinking about how electrons and atoms behave. All right, so the Bohr model is that we have electrons in orbits around the nucleus. Sort of like, so it's a classical model, so it's sort of like modeling planets going around the sun. That's the idea. But we know that that's not really what they do. But Bohr came up with it. So that hydrogen emission line, if we just go back to that idea, well, I'll stick it on there. Why not flip back to it? The idea that there were just these colors of light, these very distinct wavelengths that were emitted, rather than all the different energies, right? Only certain energies were emitted. So that's kind of interesting, right? A classical model of just it orbiting would be, well, why can't it just drop down anywhere and we should get all the colors? But that's not what they saw. And so what Bohr came up with is, let's still have this classical model, but let's add something to it. And that is that only certain orbits are possible. And I'm going to put orbits in scare quotes, right? Because we don't really think that the electron orbits the nucleus in the way a planet orbits the sun. But only certain orbits are allowed. And allowed is, I'll also put in scare quotes and underline, because it does have a specific quantum mechanical meaning, but let's not worry too much about that now. It just means only certain orbits are possible. Now, here's what the model looks like then, and anybody who's taken a chemistry class has seen this model. So let's stick the nucleus here. So that's where the protons and neutrons are. And then let's think about an electron orbiting. So it would go all in a circle all around that nucleus, right? And that's showing it in its path. And then the next allowed orbit would be a little farther away from the nucleus. I didn't get the nucleus in the center when I did that, did I? Okay, let's make it a little more noticeable. All right, so only certain orbits are allowed. That means the electron can be in this radius, or it can be in this radius, but it can't be in between. So it jumps without ever being in this space from here to here when we heat it up, and back from here to here when it emits light. And that's why we get that very specific energy. It's the energy difference between these two orbits. That's the Bohr model. And it's important that we understand this only works for the hydrogen atom. Okay? Only. It's an incorrect model, but it's a useful model. All right. So the thing that was, that came out of this, it worked really well for hydrogen, and I'm going to show the equation on the next piece of paper here. But so it was, Bohr it was awesome, right? He figured out he can actually model this and calculate the wavelengths and match it up to hydrogen perfectly well. So it worked well for hydrogen, but then found out it only worked for hydrogen. It didn't work for any of the other atoms. And so it's flawed. it's incorrect, but it was still a fundamental breakthrough. And the fundamental breakthrough was that things are quantized. These energy levels are quantized. That means they have discrete levels. Quantized, something that you can count, right? And so the idea that there are discrete energy levels where the electron can exist and not in between. And so the different, some of the things I've talked about in class to try and analogize this, or get, sorry, and I just made a verb, to try to get an analogy for this is things like steps versus a ramp, right? You can be anywhere on a ramp. On steps, you have to step on the steps. Or integer numbers versus real numbers, right? A real number, it could be anything, continuous values. So continuous versus discrete. Integer numbers versus real numbers. Hopefully you can read that. That was the big breakthrough, and it worked, and that's where quantum mechanics, which is our best explanation, came from. Our best explanation of how electrons behave in atoms. All right, so let's talk about the equation, and I don't even know yet if I'm going to assign any calculations in the homework. So I'm gonna do the equation, but it's the kind of thing where I will give you the equation if we do any, and I'll see if there's any that I want to put in the homework from this textbook or not. So the Bohr model matched the hydrogen spectrum. And I think it's, doing the calculations once, I think helps us understand the concept. The concept is what we're after. So here's the equation for an energy level in hydrogen. So it's minus 2.178, and I have to look it up. I don't have this memorized year to year. I'll have it memorized after a day or so of doing problems. So it's just this constant, minus 2.178 times 10 to the minus 18th joules, and then times z squared over n squared. Now, z is the charge, and since this only works for hydrogen, I don't really know why they put a variable there. I mean, once I'm emperor of chemistry, we'll just put a +1 in there, right? And 1 squared is 1. There's no reason for that because it only works for hydrogen. Now, when he came up with the model, he was trying to, have something more general than that. And then n is the number of the energy level. So which step are you on, if you will? And that integer number, and having it be n, that is used then throughout, not just the Bohr model, but it's used in the quantum model and all over the place. So n can be 1, 2, 3, ... right? Those are the different levels. All right, so we could draw then another energy level diagram. And once we're done with all of these, I'm going to show you a real energy level diagram for a real atom that's complicated and has a whole bunch of levels. But for the simple one, we'll just draw it like this. Energy level 1, energy level 2, energy level 3, energy level 4. And I haven't drawn this perfectly to scale. I didn't calculate it or anything like that. But you'll notice that the higher up in energy you go, the closer these electronic energy levels get. And in fact, that's why when you heat something up super hot, you get white light, because you get a continuous, all these energy levels kind of merge together. All right, so now what we're seeing is we're seeing an emission, that change in energy from maybe energy level 2 to energy level 1. So we go change in energy from 2 to 1 is equal to the energy of a photon. And they have to, the energy of the photon has to exactly match that gap. And we can do all kinds of stuff with this actually, right? So what we did, or what I did in the demo, is I heated it up and watched the electrons fall back down and got, we can also do the wavelength, and got the photon energy off of that, right? But we can also shine light on a substance. We can shine light on a solution of atoms and pop an electron up to a higher energy level and watch the light disappear, right? So when we shine light through that sample, some of the light disappears because the energy is going towards promoting that electron. That would be absorption spectroscopy. So you can do all kinds of things. Emission is what we did, where you heat it up, it pops back down. We can hit it with a laser. You can, lots of cool stuff. Anyway, so big picture is we want to understand this idea. The idea that electrons are able to jump between these energy levels and interact with light in that way. And we can use that light to probe and calculate the energy difference, but then the actual energies of those orbitals from it. So that's kind of cool. Anyway, about this equation again. So what we would do is we would calculate the energy level 2, so plug in a 2 for n, calculate it out, and then plug in a 1, so it drops out and you just get this, and then get the difference between those two, the change in energy, and that has to match. Now, don't worry about whether it's positive or negative, right? Whether you're going up or down, it's that energy difference. So kind of like the absolute value of that difference in energies matches the photon. All right, that's the Bohr model. I think that's it. Yeah. So the next thing we'll talk about is the quantum model. And that is the correct model. But again, just the take-home message from the Bohr model is that energy levels are quantized and they're discrete, and we want to understand how light interacts with these orbitals. All right, thanks everyone.